Hello, class. On this adventure in algebra, we're going to look at cyclic groups, and now we're going to study the order of an element. So given any group G and any element little g, the order of that element, magnitude of G, is the smallest positive integer n, such that G to the n is the identity element. And something we'll prove in a later video is that this is actually the size of the cyclic group generated by G. And so, of course, it's possible for the order of an element to be infinite or finite. And so, let's fix the example of the non-zero complex numbers under multiplication. And let's let G be equal to 2. As we already saw previously, the cyclic group generated by 2 is all powers of 2, both positive and negative powers. And so that set has got infinite order. In other words, if you keep multiplying 2 by itself over and over, you're never going to get 1. So it has infinite order. On the other hand, if G is 1, then the order of G is 1 because, well, there's nothing to do. You're already there. If G is negative 1, well, if you multiply negative 1 by itself, you get 1. So the order of negative 1 is 2 in this particular group. Remember, which group you're talking about matters when you're doing these calculations. Similarly, if we take the imaginary number I squared is negative 1. I cubed is negative I to the 4th power is 1, so the order of I is 4. And you can actually see when I'm doing the calculation, I'm actually writing down the elements in the cyclic group. So now let's study some properties about orders. Let G be a cyclic group of order n with generator A. So in other words, G is generated by A. And then you can ask yourself, well, when is A to the k equal to the identity? For what powers do I get the identity? Well, the only powers that are the identity are the multiples of n. And this is an if and only if statement. And this actually partly explains why we call this a cyclic group, because the idea is that as you start to compute the powers, you're actually going to get a repetition. So, A cubed, let's assume n is 3, so that the order is 3. By definition, that means A cubed is the identity. Well then, what's A to the 4th? Well, that's just A cubed times A, which is the identity times A, so A to the 4th is A. What's A to the 5th? Well, that's just A cubed plus A squared, so it's A cubed times A squared. It's just the identity times A squared. It's A squared again. What's A to the 6th? Well, by our theorem, that has to be the identity. A squared, E. So you start to see this repeating pattern. And so what happens is, as you start to compute the higher and higher powers of your generator, you're just cycling through the same list of n elements in order over and over. And so that's the origin of the name cyclic group. Unfortunately, the problem with this name is the infinite cyclic group doesn't have this pattern. It extends infinitely long in both directions, but well, sometimes you have to give a name to a mathematical object, and so we still call it a cyclic group, even though you no longer have this cycling pattern. We'll see that this example also will show us a bit how to do the proof in a moment. The other theorem we're going to prove is that given this same setup, we've got a cyclic group of order n with generator A. If you let B be the kth power of A, then the order of B is given by this formula, n over the GCD of n and k. So you can actually compute the order of every element in a cyclic group. Because remember, every subgroup of a cyclic group is cyclic. So if you've got another element, it's generating a cyclic group as well. This tells you the size of that corresponding cyclic group. Alright, so we want to prove this theorem. It's got an if and only if, which means we have to prove two different directions. Which means first we have to assume a to the k equals the identity. And what do we want to show? We want to show that k is actually a multiple of q. A multiple of n. What does that mean that n divides k? It means that k is equal to n times q for some q. That's our goal. That's what we want. Well, let's look back at this pattern. So of course, proof by example is not always allowed, but let's just assume for a moment n is 3. We see these patterns here, and what is going on? If I want to compute a to the k, what did I have to do? Well, by the division algorithm, it's q to the n plus r. A times q to the n times a to the r. But a to the qn is just the identity, and you get a to the r. In other words, if your remainder was 1, you get a. If your remainder was 2, you got a squared. And if your remainder was 3, you got, your remainder 0. You got e. And so the value of a to the k actually depends on the remainder of the k when you divide by n. And that's what we got when we did this calculation. And so that's always true. And so that's something we observe, and so we can try to use that for this proof. In other words, assume a to the k is equal to the identity, do this quotient and remainder calculation, and see that a to the r is the identity. So now that we've done a little bit of thinking, let's actually try to put verbs in our sentences. So let's try to do the forward direction of the proof. So let k be in z, an integer. Note right now I'm not actually doing the forward direction. The statement involves k to be an integer anyway, so I'm just going to do that. And I'm just going to use the division algorithm up front. Why would you do this? Well, because then it allows you to refer to q and r in both directions of the proof without having to redo it twice. So by the division algorithm, there exist unique integers q and r with k equals qn plus r, where r is between 0 and n. Now we're doing the if and only if statement. So we're going to assume a to the k equals e, and we want to prove that n divides k, which means in this case, since k is equal to qn plus r, we want to prove r equals 0. So keep in mind that's what we want. We want r equals 0 because that tells us that k is equal to q times n, which tells us n divides k, which is what we want to conclude. Alright, so let's do this calculation. A to the k is equal to a to the qn plus r. By properties of exponents, that's a to the nq times a to the r. By properties of exponents, that's a to the n to the q times a to the r. But remember, our cyclic group has order n. So a to the n is the identity element. And the qth power of the identity element is the identity element. And multiplying by the identity element gives you the other element back. So we now see that a to the k is equal to a to the r. However, since a to the k is equal to e, we have that a to the r is equal to the e. So we now have a power r that's less than n, such that a to the r is equal to e. Remember the definition of orders, it's the smallest positive integer such that a to the n is equal to e. So we want r to be equal to 0. What happens if r is bigger than 0? Well, if r is bigger than 0, well, let me use black. Then we have a to the r is equal to the identity element, and r is less than n. N is a positive integer. This contradicts the definition of order. This contradicts the fact that n is the order of r. Of a, I mean. Right, the definition of order is the smallest positive integer such that this equation is true, and you just found a smaller positive power. And that's not supposed to happen. So, whoops, we have a contradiction. The only way out is that this additional assumption must be false. So r must be 0. What does that mean? Well, that means that k is actually equal to q times n. Hence, n divides k like we wanted. Congratulations, that's the halfway point on this proof. We managed to assume that a to the k is equal to the identity, and we concluded that n divides k. What do we still need to do? We need to show what happens with the opposite. Supposing n divides k, conclude that a to the k is the identity. Well, now let's do the reverse direction. So now we're assuming n divides k. So suppose n divides k. We want to prove that a to the k is the identity. Well, a to the k is equal to a to the qn plus r. Wait, where did this come from? Oh, that's right. This was my decision to use the division algorithm before I started in on the if and only if proof. Right, if you remember in my setup paragraph at the very beginning, I started with let k be an integer, and then I did the division algorithm right at the very beginning. And I point out one reason why I wanted to do that was because then we could take advantage of it later. And here's where I'm going to take advantage of it. So k is equal to, in other words, this is just copy and paste the exact same calculation we already did. So repeating the same calculation we've already done, but a to the k is equal to a to the r. This is true regardless of whether or not n divides k, which suggests that I actually could have edited the proof even further and made this a lemma, but oh well. So a to the k is equal to a to the r. Since n divides k, r is actually 0. Because k is equal to q times n plus r, and by the division algorithm, and so by definition of divisibility, the only way you could actually have divisibility here is if the remainder is 0. And so a to the r is equal to a to the 0, which is by definition e. So a to the k is equal to e. So that direction of the proof is actually easier. And so this is one way to do this direction, by taking advantage of the division algorithm right off the bat. If you don't like this approach, another approach you could have done was suppose n divides k, and then you would do the usual bit where then you would say that k is equal to q times n for some q. And then you would do the usual arguing. So you could do the proof this way too. And it's also true. It's also true and correct. And so the preference is yours. I chose one way because I wanted to convey the idea that sometimes if you set up your proofs right, you can actually include steps before you do an if and only if statement and use those steps in both parts of that if and only if proof. And sometimes that can be used to simplify matters. In this case, this is actually shorter. The reason why I actually did that is because copying and pasting is a lot easier than writing more than once.